Okay, so number 13, the rate at which the distance between the road and the edge of the water was changing during the storm is modeled by F of t. Okay, so F of t is you have the water in the road. Okay, and this is the rate of change in which the distance between the road and the water is changing. Okay, and it's meters per hour. Okay, the edge of the water was 35 meters from the road when the storm began. So initially, it was 35 meters from, okay, so that's my initial value. And the storm lasted 5 hours. And they even give us the derivative. The derivative is that. Okay, so this is actually the second derivative of the meters. Okay, so you think about the velocity, acceleration. What is the distance between the road and the edge of the water at the end of the storm? Okay, so we want to know the distance between the edge of the water and the storm. So if you want to think about this is what it's changing. Okay, so this is how much it's changing. So the distance that it changed between the water and the storm is going to be from 0 to 5 square root of t plus cosine t minus 3 dt. Okay, and that turns out to be negative 8.5053 meters. So that is how much the distance between the water and the road changed. It changed by minus 83503. Originally, it was 35 meters. So the distance between the road and the edge of the water is now at 26.495 meters after the storm. Probably using correct units, interpret the value of f prime of 4, which is 0.007, in terms of the distance between the road and the edge of the water. Okay, so what this means, since f prime is the rate of change of the distance between the water and the road, it means that the distance between the road and the edge of the water is increasing because it's positive, so it's going up at a rate of 1.007 meters per hour squared because it is the second derivative. Okay, so part C, at the time during the 5 hours of the storm, at what time during the 5 hours of the storm was the distance between the road and the edge water decreasing most rapidly? Okay, so in order to do this, we need to find the minimum. So decreasing, so we want to know at what time was the distance between the road and the edge of the water a minimum. So we need to find the derivative of f, which we have, f prime, and we're going to set that equal to 0. Okay. So x turns out to be 2.840. And if you would graph this on your calculator, you'll see that it's going from a negative to a positive. So that would be a minimum. Okay, part D. After the storm, the machine pumps sand back into the beach so that distance between the road and the edge of the water is growing at a rate of, okay, so this is the in. So now we're pumping sand back in, so this is my in. Repeat the number of days since the pumping began. Write an equation involving an integral expression whose solution will give the number of days the sand must be pumped to restore the original distance between the road and the water. Okay, so this represents the change between the water and the sand. Okay, so this represents the sand. And this represents the integral from 0, call it x. Okay, that represents how many days we're going to start pumping in back water. So that represents how much sand got pumped in, and we're going to minus the storm. This is how much the storm so that would represent my equation.